Hello, this is Julius Marshall, and in this video I will briefly present a novel guidance system for tactical mapping, published in Chapter 3, titled Autonomous Multi-Rotor Unmanned Aerial Vehicles and Tactical Coverage, of the book Control of Autonomous Aerial Vehicles, Advances in Autopilot Design for Civilian UAVs. We want to explore an environment and gather information about it using cameras with an autonomous UAV in a manner that minimizes its exposure to potential adversaries. In the coverage literature, there are very few well-known paths that can be used for coverage, such as the booster feed-in path shown here. However, we can't use paths like these because they don't inherently allow us to exploit obstacles for shelter. So, we will apply our tactical path and trajectory planning algorithms to explore the environment. However, there is one piece missing, and that is a way of generating goals for the path planning algorithm that lead the UAV to unexplored sections of the map. Many features of the proposed guidance system for mapping. Most notably, the user can define either a reckless or tactical behavior when deploying this system. In reckless mode, the UAV will essentially proceed towards its goal point along the shortest path. In tactical mode, the UAV will exploit obstacles for shelter as it proceeds towards the goal. Also, we propose a novel goal selection algorithm which will enable autonomous exploration of the environment. The proposed mapping system can be used to provide situational awareness for many organizations by gathering information discreetly, observing wildlife in a way that doesn't disturb them, and for search and rescue operations. The tactical mapping system is split into multiple modules. Upon receiving a pose and a voxel map, the goal selection algorithm, which is based on the octree technique, is designed to differentiate clusters of explored and unexplored voxels and select goal points among them. The path planning algorithm is based on the LPA star technique and employs a custom tunable cost-to-come function and heuristic function to enable tactical or reckless behaviors. The collision avoidance or constraint generation algorithm is not covered in this paper. The trajectory planner is based on the fast model predictive control technique with a custom cost function to also enable tactical or reckless planning. The following video will show the results of a simulation where the proposed mapping system is set to generate goals in a greedy manner and plan motion tactically. The vehicle starts at the green star. Its trajectory is shown by the red line, the planned path is shown by the blue line, and the planned trajectory is shown by the green line. The goal point is denoted by the blue star, and the pink and yellow shading indicates the projection of the explored set onto the XY plane. The two subplots on the right show the XZ and YZ projections of the explored set respectively. This is shown to give a more complete idea of the set of explored voxels and how it evolves throughout the simulation. In this simulation, the goal selection algorithm's parameter set results in the generation of a sequence of greedy goal points. And by greedy, we mean goal points that lie in areas which have a high potential for information gain. Due to this configuration, the first goal point is on the second floor of this two-story environment. The path planner finds a path which avoids intersecting the ceiling in an area near the explored set, but eventually the search algorithm reaches the unexplored area of the map, and the path goes to the second floor, however bypassing the staircase. The proposed mapping system has several mechanisms to prevent the vehicle from colliding with obstacles, including an algorithm which determines collision avoidance constraints for the trajectory planner, a ray tracing algorithm which determines if the shortest line joining the UAV in the next waypoint is collision free, a goal safety algorithm which forces the path planner to take alternative routes if the goal point lies in an undetectable region above or below the vehicle, and a condition which triggers the path planner to resolve the collision once it is discovered. As you can see, in many instances the vehicle closely follows obstacles, which provide it shelter as it proceeds towards the goal point. Once the vehicle has explored roughly 97% of the environment, the mission is considered complete. In the following video, we will show the results of a simulation where the mapping system is set to generate goals in a systematic manner in contrast to a greedy manner. In a systematic approach, goals tend to be the closest unexplored area of the map, but do not necessarily lead the vehicle to areas which have a high potential for a large amount of information gain. Furthermore, the system will plan motion recklessly, and that is It will not consider proximity to obstacles in the path plan, but only to avoid collisions. In some instances, you may see the planned path and the vehicle's trajectory not overlap, and this is typically due to replanning occurring at the same time that the vehicle is aggressively tracking a planned trajectory. Furthermore, you see paths intersecting occupied voxels, and this is merely due to the fact that the simulated navigation system has not seen those voxels, and unseen voxels are defined as unoccupied. The vehicle's mission is complete once it has explored 97% of the voxels. As can be seen, since the vehicle's motion planner is set to instill a reckless behavior, it explores the environment autonomously but does not incorporate the positions of obstacles into its motion plan, besides for collision avoidance.